Subscribe and press this bell icon to never miss another lecture video. Hi, welcome to GATE ESE Lecture. We're in lecture number 71 and we are still in the module of Fourier transform, continuous Fourier transform. Until now we have discussed almost all the concepts, all varieties of questions that might ask in GATE exam or ISRO exam or IES exam from Fourier transform point of view. Okay, and this is the very important, one of the most important and one of the most crucial concept that we need to discuss now. That is a concept of ESE and PSU and Parseval energy theorem or Rayleigh energy theorem, Rayleigh theorem, anything that you can say. What are these concepts? I think when I was discussing the property table at that point of time also I gave you some kind of hints over there, but that is what we are going to discuss here. Very much important for your GATE exam and ISRO exam. We'll discuss a ISRO question also in the next video lecture, but my dear friend, please be careful. In lecture number 72 I'll discuss this question from ISRO exam, and that will going to give you a lot of clarity on autocorrelation function, cross correlation function, all of those things that we are going to understand. Very much important. Do not miss a single video lectures from now onwards. Now let's start with before getting into this concept, energy spectral density and power spectral density, I forgot to share with you a very important question type. It's a very simple, easy question from bandwidth concept. You can quickly solve this thing, but let me solve it for you, and please do understand the actual concept behind this question. So it is asking find the bandwidth of y1t and y2t and yt. Sir, y1 y2 y kahan pe hai? y1 yt is here, y1t is here. I forgot to write it down, really sorry. y1t, y2t and yt is here. These are the outputs of the subsequent systems, and this is the transfer function of the system. This is the transfer function of the system. So these are the transfer function. This h of omega, it is in this frequency domain na sir? Ha sir, these are the inputs that we are giving to this respective system na sir? Absolutely correct. Sir, what is this? What is he is asking, sir? I think I can calculate the bandwidth of y and t is nothing but by taking the convolution of these two. I can calculate the bandwidth, sir. By taking the convolution of these two, I can also get y1 omega and also y2 omega. I can calculate y1 omega and y2 omega by taking convolution of these two functions. After taking that, we can, from y1 omega and y2 omega, I can also calculate the bandwidth of this respective signal. But my confusion is, sir, ki how to calculate the bandwidth of the convolution of these two signals. वो थोड़ा सा कंफ्यूजिंग है. चलो एक एक करके सारे चीज सॉल्व करते हैं. पहले लेट मी स्टार्ट विथ कैलकुलेटिंग द व्हाट इज द फोरियर ट्रांसफॉर्म ऑफ डेल ऑफ टी. सर, डेल ऑफ ओमेगा, सर, I'm sorry, what is the Fourier transform? That is del of omega. What is the value of this del of omega? That is, sir, 1, sir. Absolutely correct. I'm sorry, this is del of omega is wrong. You can write down in this way: Fourier transform of del of t, that is nothing but 1. So you can, so I wrote it here, no, I'm really sorry. And this is the Fourier transform of x of omega. Fourier transform of h omega is given. Listen to this carefully. X of omega is given 1. So x of omega is 1 and h of omega is given a gate function. Okay, gate function. What is a gate function, sir? Rectangular pulse ना. हाँ, इसको हम बोलते हैं rectangular pulse. I'm sorry, rectangular function. You can call it as rectangular pulse. You can also, I'm sorry, rectangular function. You can call it as rectangular function or pulse function, okay, or gate function. Please remember this, okay? Rectangular function, pulse function or gate function. Okay, now if you have a gate function like this, which is whose width is t, Okay, now and its magnitude is a. Okay, now you can write down this in this format: a into g of t. Okay, whatever the domain is, time domain for example, then t. If it is a frequency domain omega, you can write down here omega. So a g t t. What is this t? T is nothing but width. So that means 2 into 10 to the power 4 pi is the width. Will be the width of this gate function. Kya? Absolutely correct. Okay, you understood this concept. So I am now going to call this function as gate function. So you can assume this gate function is nothing but rectangular function or pulse function. Okay, now quickly solve this thing. सर आप बहुत बोर कर रहे हो सर, ये जल्दी जल्दी आपको बताना है ना सर, हमको फिर जाना है वो वाले सब्जेक्ट में ना, एनर्जी स्पेक्ट्रल डेंसिटी, पावर स्पेक्ट्रल डेंसिटी में. हाँ जल्दी जल्दी ख़त्म करते हैं. g 10 to the power 4 pi omega, g 10 to the power 4 pi omega. So क्या हो जाएगा ये g 10 to the power 4 pi omega. Sir this can be represented as 10 to the power 4 मतलब सर 10,000 होता है सर, 10,000 होता है सर. हाँ, so this will be minus 5,000 pi minus 5,000 pi to plus 5,000 pi. And the magnitude is 1, I think, yes. So and the domain is omega. So this is your h of omega. This is your x of omega. X of omega is 1 and h of omega is this. X of omega is 1, h of omega is this. Now the convolution, the y of y1t to y1 omega, then y1 omega will become what? y1t. The Fourier transform of y1t is nothing but y1 omega. Fourier transform of y1t is nothing but y1 omega, where y1 omega is given as x of omega into h of omega. Yes or no? हाँ sir, because y1t is xt convolution of h of t. That means in frequency domain that will going to x of omega into h of omega. You understood this concept? हाँ सर समझ गया सर, ये कॉन्सेप्ट सबको पता है सर, बचपन से सीखा था सर हमें कॉन्सेप्ट. x of omega into h of omega. x of omega is given as 1 into h of omega is given like this. So h of omega is ga of, what was this, 10 to the power 4 pi omega. So what will be the value? Sir वही हो जाएगा सर, वही गेट फंक्शन हो जाएगा सर. Absolutely correct. So you can see this came out to be your y1 omega. Very important concept, my dear friend. It looks very scary, but the solution to this question is extremely easy. Okay, now what we got here from this y1t perspective, so the y1t, the output y1 omega that we got here, y1 omega that we got here, na, this y1 omega, that is this function that we got. So what is the bandwidth that we can see from this y1 omega? This is nothing but your y1 omega. Now what is the bandwidth that you can see? Sir, clearly it is seen that bandwidth is this much of 5,005 is the bandwidth, sir. Bandwidth of y1t is nothing but 5,000 pi. Clear this concept, how we solved it? Okay, now second thing is a little bit tricky part. What is the tricky part? You can see here, this is the first case. Okay, I'll take for the second case in the next slide. For the second case, you can see here your x1t, which is given here, it is a gate function, and here it was given a impulse. So you quickly calculated the Fourier transform of this impulse function as 1. But in case of a gate function, the Fourier transform of this gate function will come out to be a sinc function. Yes or no? So in the second case, I can write down 10 to the power 4 g of 2 into 10 to the power minus 4 of t. Then I think this is the question, no? 2 into 10 to the power minus 4 t 10 to the power 4, right? This is the question. Now this is your x1t, right? This is your x1t. Now what is the Fourier transform of x1t? That will be x1 omega. So that will be x1 omega, which will be given as, sir, that will be given as the area into sinc width by 2 into omega, sir. This is width, sir. Width by 2 into omega, sir. Absolutely correct. Now 10 to the power 4 look here carefully.